Hi, everyone. My name is Sancha Norris with Intel AI Marketing. Thank you for joining us today in our GenAI webinar series. We have a guest speaker from Accenture today. Intel and Accenture have been in a deep partnership for over 13 years now, and we really appreciate their working with us. And today, our speaker is Richard Jung. He's a data scientist from Accenture Applied Intelligence Units. He's been helping enterprise clients build and deploy AI over a wide range of industries. And specifically in the past year, he's been focusing on building customizable Gen AI solutions using open source models. He's received his PhD in computer science from UC Santa Barbara and his bachelor's from Columbia University. So Richard's presentation will be about 40 minutes. And then we'll take Q&A after that. So be sure to submit your questions throughout the presentation. And this session is being recorded, and it'll be available on demand right afterwards. So without further ado, I'll turn it over to Richard.
All right. Thanks, Sancha. So just to reiterate, I'm Richard. I'm a data scientist from Accenture's Applied Intelligence Division. And I kind of want to talk to you guys about some of the work I've been doing over the last year on building generative AI platforms. So when we say generative AI platforms, what we kind of mean here is just like a high-level architecture of how an enterprise or a team can better control and enable the use of generative AI models. So this includes things like enabling developers to build secure and safe applications using generative AI models. And also something to my interest is sort of hosting generative AI models on custom hardware. The goal of today's talk is that by the end of it, you kind of have an idea of why building a platform might be a good idea, and also to demystify some of the generative AI models out there so you can start serving them from a platform on your own. So to kick things off, I kind of want to start off by just looking at generative AI from a high-level perspective, see how it fits and how we use data and models in our organizations. So at the base of just using data and models, we have descriptive and diagnostic methods. And these kind of methods, you're really using data to find answers to very specific questions that you might have. And using these kind of data points, you make plots and visualizations or modeling and statistics to really get at the heart of what might be some causal relationships. Over time, we've kind of introduced new types of methods where now we're using data and models to build these prescriptive and predictive methods. And the difference between this and sort of the descriptive and diagnostic methods as we see it is sort of these prescriptive and predictive methods are more about fitting data to models in order to do something. So this might be more of the machine learning and data science fields where we might do something like fit a classifier to identify specific parts, or maybe build text summarizers for specific types of documents. And the real focus here is that when we were building these kind of software components, we are really training specific models in order to do a narrow subset of tasks. So we're using machine learning methods and really building out these kind of very specific applications, which maybe one or two teams might be using, or something that we can really tackle specific tasks with. And that kind of leads into where we are now with generative AI. Now we're less focused on training models ourselves, and we're kind of relying on these massive models that are hosted and trained by some other groups with a ton of data. And we're kind of using them as just these black box Oracle systems. We're using these pre-trained models. If in the past we wanted to do text summarization, maybe we'd be training our own models, but now we're kind of relying on these endpoints in order to kind of satisfy the same application purposes, right? So for example, if you're building a text summarizer before you train the model, and now you're just calling an OpenAI endpoint and a large language model in order to do the same exact types of tasks. That's not to say that the other types of the ways we use data and models is outdated. We still need to use those in order to get the best value out of our data and models. So generative AI just kind of represents a different subset of applications. It's more about automation and doing these things where we can just rely on these black box systems and we just verify the results. So let's take a look at some of the different types of generative AI models out there and the modalities that they deal with. We generally categorize these based on the type of content that they produce. And it's a very application focused kind of mindset rather than data or focused. So we have text. We might have something like GPT or Llama or Gemini. Code generation. We have models like GPT as well, also text-based. There's some models that are fine-tuned on or specifically tuned on code. So Code Llama and Codex. Image synthesis, we have models like DALL-E and Stable Diffusion. And one thing I want you to note here is that these are very general purpose models, right? They handle text, but they're not specifically focused on any particular task. Voice synthesis, we might have something like OpenAI and Whisper. And there's a lot more out there for different specific domains. One thing is this slide is already kind of outdated because the field is moving so fast. Almost daily, we're seeing new models come out. I think last week we had Sora, which is like a mind-blowing model for video generation. And just, this week we had Google release some new models called Gemma. And they updated their Gemini to increase the context window. So these kind of things, change all the time. The one thing I kind of want to point out again is that, we're using these models as tools, right? We're no longer training our own models when we're working with generative AI. We're kind of using these in a very general purpose way. And that's kind of important in the way we architect our systems. So all these modalities kind of enable different applications like sales writing for text. They're kind of, in a sense, interchangeable as long as the quality is the same. Just to give you a little bit of perspective on what we're doing at Accenture, we've kind of identified some of the most common generative AI applications that cover both the front and the back office. So from the front office, we've seen a lot of situations where people are using generative AI for marketing editing and visual content creation, where they might be prototyping different marketing materials to optimize for search or style. They also might be trying out these text models to generate different product descriptions, or some of these image models to touch up existing information or touch up existing images. In the back office, we see the more common applications, for example, AI enterprise chatbots and various types of copilots, which use generative AI to help employees, search documents or help customer support agents make better and more informed decisions on the fly. In 2023 alone, Accenture has done over 300 generative AI projects, and we're seeing a lot more come down the pipeline today. So momentum has definitely not stopped within enterprises, and it's only expanding the need for using these models. Through all these projects, we also have our generative AI group, who has defined somewhat of a core set of capabilities that we can use to help enterprises get started with generative AI. And this kind of covers like the different types of tasks and maturity levels. So at some point you have to start with data collection and pre-processing. Maybe they want to do some fine tuning, content generation via prompt engineering, verification of the response quality when using these large language models, measuring content quality, responsible AI, managing digital assets, and finally integration into production environments, whether that's through A/B testing or sort of integration testing. All of these tasks kind of require this human in the loop factor, where you're trying to sort of reiterate or iterate upon different ways you're using it. So it's not just this automated process that we kind of think it might be. With that perspective on generative AI being so prevalent in all these fields, kind of want to now start talking about the main topic of today's talk, which is building a generative AI platform that can ease these steps within an organization. And again, a generative AI platform here is just a high level architecture of how we see an enterprise or team can better control and enable the use of generative AI models within their organization. So the first thing we did when we were trying to build a product like this is just kind of look at the different possible challenges that might come with working on generative AI, especially since we're working on self-hosting these large language models. We kind of focused in on the different end-to-end difficulties that might arise. So some of the challenges we identified were from computational cost of running generative AI models, because these are very large models that require kind of specialized implementations in order to work in your environment, to also integrating these generative AI models into different applications within someone's live environment, right? It's not always so clear how to integrate these applications together. To also trying to address responsible AI concerns and ethical concerns when working with these types of models. Because they're sort of these oracle models trained by other groups, they come with a lot of safety guidelines and guardrails that we might have to take into consideration when an enterprise decides to use one of these solutions. So our goal was to really build a template for how we might implement a system that eases some of these concerns. And let's take a look at what we kind of decided upon. So at a high level, how we designed our generative AI platform is we started at the top level where you have the users. And these are the people who directly interact with your platform in order to build out applications. All of these users, just going along with how we identify generative AI in data and models, is all of these users are more or less using the same set of models to build out their cases, often using things like prompt engineering to change the way the model outputs things. But fundamentally, they're all using the same set of models. So if they're doing classification, summarization, chatbots, agents, they're all kind of hitting the same type of large language model endpoints. So those large language model endpoints have to be very, reliable and always up. So this platform that we're trying to build is responsible for enabling access for these users to the generative AI models. And the way we decided to allow them access is through a gated set of user service APIs. So this is basically how, if an application developer was using something like OpenAI's GPT API to build an application, it's very similar to calling that, but by having this additional layer on top, we can kind of implement different levels of compliance and organization depending on what the needs of the enterprise might be. So these needs are put in the subservice layer, and this layer represents everything that might need to be done to a request before they hit the model and the actual compute. By having this kind of layer where you kind of have this nebulous array of tasks that you might want to do. For example, you have something like security and compliance monitoring. If you want to filter certain queries and make sure no one's leaking data, you put them in this layer. This layer is pretty, open-ended. You can have any number of things. We've seen people start building models in this layer as well, where these models are sort of this like narrow individual task just to like find out, like maybe take a prompt and predict which model to use, or maybe take a prompt and predict whether this will be a harmful model. All things that are basically put there in order to filter out prompts or clean things up or direct things to where they need to go before they actually hit the compute or the external APIs. So at the heart of this is the compute layer. And since we're working with self-hosted generative models here, we're kind of putting it at the forefront. but these are the final set of direct APIs for the models that will be deployed on your platform. You can host any variety of models here, depending on the types of applications you want to build. You can host large language models, image generation models, embedding models, multimodal models, anything out there that's sort of like serving the purpose of generative AI, where lots of people are using the same model for different purposes. The caveat here is that when you're self-hosting generative models, the resources here are expected to be managed in order to control costs, scalability, and usage, and everything good like that. Of course, the flexibility of this pattern or of this platform is that it allows you to access proprietary APIs as well. This gating layer kind of allows you to direct queries to where they need to be. So sometimes some of these proprietary models have much better quality than the open source models. So for certain sensitive applications where quality is really, really important, you might want to still allow access to certain external models like OpenAI or Gemini or anything like that. From a user perspective, the goal is ultimately that they don't have to worry so much about models. They don't have to worry about what type of model to call, what kind of hardware it's running on, or compliance factors, and they can just focus on building the best type of applications that they can. I want to point out, this is not too convoluted, and it's kind of like the natural solution you come up with yourself if you want to build a platform that has these levels of compliance and security. It's just a framework that we found helpful to help organize how you look at things when you're trying to, when users are trying to use this platform. I want to run a quick poll. So I'm going to switch it over to Sancha for now.
Yes, hi, thanks, Richard. We're going to take a quick poll right now to gauge what our people in the audience is doing with regard to building GenAI platforms. For the external model option that you see here, check that if you're using a paid service. I think we're going to assume that everybody is using a free version, or has used that at some point in the past. So we're interested here if you're using a paid service. And then for the self-hosted, that can be if you're fine-tuning a pre-trained model, like what Richard was talking about with the many open source models that's available now. If you're building a platform that includes prompt engineering or inferencing platform from edge to cloud, we're interested in what you're thinking. Have you built one, or are you planning it? So I'll just give another few seconds, and then we'll go to results. So it's very, I guess it's kind of even across the board. Some are using external models. I actually thought it would be a higher number, and quite a few are you're building your own or thinking about it. So that's great. I think you're in the right place. I think Richard will be able to share the pros and cons. There are definitely pros and cons between going straight to a external third-party model versus building your own. And I'll let you expand on that a little bit more, Richard.
All right. Yeah, thank you. I'm pretty surprised by the results. I guess I shouldn't be so surprised considering the stock price and performance of some hardware vendors these days. But yeah, it's interesting that so many people are also thinking about self-hosting models as opposed to just using external models as well. Let me load my slide for a second. Okay, so one of the things that I want to talk about is sort of the benefits of using self-hosted models. A lot of this talk, the remainder of this talk, will kind of focus on self-hosting models and the challenges we found because, as I mentioned, the above platform architecture is not so unique or different from how you might deploy some other services. So the real difference when you're doing with generative AI is how you can possibly host these large models and what kind of computational bottlenecks they might have. So let me start off with just kind of talking about the four different factors that we kind of identified as why you might want to self-host generative AI models. And maybe I can convert some of the people who aren't thinking about it over. One is ubiquitous compute. One of the biggest driving factors that we've seen from our clients is that they kind of want to deploy generative AI applications and solutions everywhere and on all different types of devices. This kind of means like putting generative AI in scenarios you might not think about it, like, on edge devices, on different types of cell phones, mobiles, even, on the edge or in data centers. All of these different places should have some kind of generative AI models within. And by kind of self-hosting these models, you can kind of have this option of deploying these models everywhere you need and kind of sharing this compute resource with different kind of angles, right? So because these are general purpose compute machines that you kind of own, sometimes you might want to build additional layers on top, such as like the responsible AI layer that was based on training different models. The second benefit is sovereignty. And this is probably what most people are thinking about when they're thinking about self-hosting models. And that's sort of the ability to own everything that you're using. If you rely on something like OpenAI or Gemini, those are great models, but that kind of locks you into their development cycle and their kind of release cycle. If you want to implement some responsible AIs at a different level, you're kind of bound if you're using a proprietary API. For example, I think OpenAI already has some kind of safety guardrails built into their queries. So maybe in some situations, you'll be bound by the internally built things that OpenAI does that might lower the quality of certain responses. Also, this is the most secure situation for data sensitive users. We've actually seen this with some clients where they want to host their own models because they don't want any sort of leakage in the outputs produced by the model. So they might want full control of the data and build additional compliance layers. The next thing is rapid deployment. So speaking again about vendor lock-in, the benefit of self-hosting models is that you have the access of all of open source and new technologies that are coming out today, since you're responsible for the hardware. This also lets you make decisions and change things around as you see fit as fast as you want, right? You don't have to wait for services, or maybe if services are changing and you don't want to deal with certain things, you can just quickly switch over. And one of the biggest points here is actually cost efficiency. And going along with everything else, deploying your own set of models means you can you kind of control the cost to a degree, right? If you need to scale up or down depending on the usage or different machines becoming available or different hardware becoming more or cheaper, then you can easily do so if you self-host your models. If you're using a proprietary service, you're kind of stuck with the price that they set for you. Whereas in the long run, self-hosting some of these large language models or generative AI models might be beneficial to save something based on a per token basis. So these are sort of the four main driving factors about why you might want to self-host models as we see it. And hopefully this kind of convinces some of you that it might be worth looking into self-hosting models as well as using proprietary APIs. So we're not kind of trying to sell it as a either or situation. It's more of a complementary thing where self-hosting can be used in addition to proprietary APIs. One thing I do want to note is that proprietary models at this point, if you're working with open source, you'll kind of realize this, but proprietary models right now generally do offer the best quality a lot of the times. So OpenAI might be like the best quality for every single individual task, GPT-4, but you're kind of paying a premium for them. So I want to quickly jump back and let's take a look at one of the sample generative AI platforms that we built out using self-hosted generative models. So at the top layer, you can kind of see how this follows our pattern, but with some modifications. At the top layer, you have the applications that we built out, and we have 3 different generative AI-based applications. We have a chatbot, a knowledge retrieval system, and a document Q&A system. So each of these applications use the same large language models, which we enable through a single consumption layer where the users can choose a type of model they want for their purpose. We put this control plane in place where we kind of divert requests based off of the type request to different endpoints that we host. The subservices layer, right now it's very loose, but we do have a few constraints around responsible AI where we're trying to just record queries. The hardware layer, we actually, because we're working with Intel, we host all of our models on Intel hardware. This is managed through a MLOps platform called Converge.io that we customize a little bit to serve large language models as endpoints. This lets us access to auto scaling and all of those good factors in order to better maintain your hardware. The hardware that we are using to serve these models is a mix of high performance accelerators and general purpose CPUs. So we have the Intel Gaudi 2 accelerators for high-end expensive workloads with strict latency demands, such as Llama 2 70B. And we have the Intel Xeon for other workloads. So for example, some models like Llama 2 7B, which might be less powerful, but runs on a good enough time scale for the users, we can divert that workload to the CPUs and still get good responses. On the side, we have some additional supporting elements like vector databases and document stores, which we put separate from our immediate platform, but are still critical to building applications. We just decide to host them on the side because it was just more convenient for us. But we can easily put this directly into the platform as well. For fine tuning, this is sort of a unique situation. Right now, we have it so that fine tuning has a separate set of resources just because the computational requirements are much greater than just inference itself. So we didn't want our users to have to fight over resources for inference jobs. So we kind of set it as a side piece where it follows a job queue. Users submit jobs, and then we're using the Gaudi 2s to fine tune these models to be deployed in the inference environment afterwards. So you can kind of see like this thing we built out generally follows the template that we have set up, where we have a single point of entry and we have these layers that control it on self-deployed hardware. But you can kind of see how there's quite a bit of flexibility in where you host things and how you run things. And of course, the devil is in the details, right? How you connect all these pieces together is really where you're going to be spending most of the work. This structure is just a structure. Everything to implement it is a little bit more complicated. So in this environment, how we visualize people using it and how we see users consuming our endpoints is we can take a look at something like a RAG workflow. So if you're not familiar with RAG or retrieval augmented generation, the gist of it is that we want to build a system or application that can leverage large language models to answer user questions in a more factual way by introducing pieces of content from some documents or basically external information without having to fine tune the model at all. I'll explain it in a bit greater detail later on. So in the system, how this works is that first the user submits the query to the vector embedding model that we host on the Xeon. So embedding models are generally pretty quick to run. So we don't need to use an accelerator in order to embed a query based on the demand in our system. So the user calls our embedding endpoint, which we host, and they get a vector embedding back. They can take this vector embedding and hit the vector database where they're doing a retrieval task to retrieve the relevant documents to that query. Then once the relevant documents are returned, you do the augmentation step and you submit that query with the context as a query to the large language model in order to generate a better answer for the user. Here we're using a large language model. We decided to use Llama 2 70B. It seemed to give the most reliable results. And using a Gaudi 2, we were able to get results in or spit out tokens in a very fast and reliable fashion. So from the user perspective, they see the results, these two API calls to the embedding model and the Llama 2 model, just a couple API calls when you're actually building the application. All these side pieces under the hood, they could have several layers of compliance and optimization going through, but by passing through the system, we can enforce certain optimizations or certain use cases a little bit better. People don't have to worry so much about what model they're hitting, and we can engineer on top of that. So I'm going to switch gears a little bit here and really go more into depth of what I feel was the most difficult part of building this platform and what I've been personally working on in the last 6 months. And that's sort of figuring out how to host your own generative AI models on your own hardware in a scalable way. Again, this platform's not so novel. It's really the difference between this and most other deep learning and machine learning model deployments is just how these models itself, large language models, image models, scale differently. And to do that, we kind of have to understand a little bit about how they get the results that they get. As a brief aside, the hardware that we're using for building our platform is a mix of Xeon CPUs available on AWS and Intel Developer Cloud, and also Intel Gaudi 2 accelerators also available on Intel Developer Cloud. We found that these resources could actually help us get large language models up and running really quickly in a scalable way on both CPUs and Gaudi 2. We had to use some good software packages out there like the Intel extension for Transformers or Optimum Habana to optimize these models. But once we optimized it, then they ran pretty quickly. All right. So now let's switch gears to what I want to talk about, which is self-hosting generative AI models. So I've spent enough time talking about the general idea of a generative AI platform. And what I really want to talk about is the complexities of deploying different types of generative AI models on your own hardware. And what this encompasses is sort of understanding the workflow when you're calling a large language model or an image model or doing some kind of fine tuning or even multimodal models. I've broken it down into these 4 different types of tasks. RAG and fine tuning is kind of different than deploying large language models, but it's popular enough to warrant its own little category. And I briefly want to give you some, learnings that we had and we had to understand in order to understand why it's computationally difficult to deploy these and what kind of tools we can possibly use to make it easier. So let's get started with large language models. Most people here are probably familiar with using large language models. The basic idea of them is that there's some model out there that's been trained on enough data that they've picked up the ability to reason about certain tasks using purely text. And by interacting with that model using prompts and prompt engineering, we can get it to do some really cool stuff without having to explicitly train it. As a result, we've seen a bunch of different information or applications like intelligent chatbots that can answer questions accurately or creatively, depending on how you configure it, to more advanced use cases with LLMs making decisions and calling tools to accomplish tasks in sort of a closed loop way. The primary thing here is that one model, one LLM, has many different use cases, all configured based off of prompt engineering. So what's the computational challenge with large language models? Well, in order to get such good behavior, one of the key factors was that they found that you had to make these models really, really big. You had to train it on a ton of data and you had to make them big enough that they can pick up general purpose tasks. So here we have listed out some of the open source models out there and just the general size of them, right? The second column is the parameter count. So for example, Llama 2 comes in 3 different variants. You have a 7 billion parameter model, 13 billion parameter model, and a 70 billion parameter model. If you were to store these models in 32-bit floating point values, then the amount of space they take up is pretty massive, even for the smallest model. So for example, like the 70 billion model is about 270 gigabytes in 32-bit floating point values. To give you a little reference, A100 has up to 80 gigabytes of VRAM, so you can't even possibly fit that in there. Yet we're still running them to a good capacity, and they're still producing results in a way that we seem to really like. And the computational issue kind of gets exacerbated because if you think about the way that we kind of interact with these large language models, if you've ever used a chat style experience like ChatGPT, you'll see that the most annoying thing would be if you reach the end of the tokens that are being spit out before it finishes. So you're waiting for the next token and you're waiting for the full output to come out. Right now, the engineering work and the deployment has gotten it so that it's spitting out things faster than you can read. And that's sort of what we want. But the problem is that's a latency demand. If we want low latency for huge models, we need massive compute in order to run it efficiently. So the computational issues really come about when I'm spending a little bit more time on large language models because that's the most popular modality. But if you look at large language models, it's even more insightful if you look at how a single request is populated or processed by large language models. So we generally say that large language models generate results auto-regressively, which means that they use the previous round's output as input for next round. So let's take a look at this little flow here. You start with the user prompt, which gets passed into the large language model. So this means that it has to get computed through the entire massive model that we just talked about. The output of that single new token, or output of that step, is just a single new token. So that single new token is then concatenated back to the original input, and that process is repeated again. It's fed back into the large language model to generate the new token. This algorithm is sort of repeated until you generate something called a stop token, which is specialized to the large language model. So basically, in order to generate more and more tokens, even if you pass in a very, very large context, you have to call the model repeatedly over and over again. And it could be a very slow process if you have a lot of tokens to generate, right? Every time you're doing this, you're taking up the compute resources in order to generate the next one. So the observations that we have here are first that each token generated is one call to the expensive model. A little tricky thing about transformer-based models is that the memory usage actually goes up per token. And this is due to something called KV caching. If this wasn't the case, you'd actually have very, very, very slow responses. Each token generated would be the same cost as if you were generating the very first token, and growing actually. And this is why you're seeing a lot of issues with context size when it's, we're sort of restricted in certain situations to, 32K tokens, right? I think Gemini just put out something about 1.5 million tokens, and that's sort of mind-blowing how they engineer that, and we'll have to see how that's actually done. And finally, the last thing is sort of the total inference time can take a long time. You might not notice this because with the way that these chat interfaces work, they're streaming out tokens as soon as they come available, right? But if you measure the total time it takes to generate responses, they can actually be a lot longer than you perceive it to be. And what happens here is if you're serving this very naively, if you're, doing it turn by turn, you're serving one request at a time, then it'll actually be very, very, very slow. You never have any users if you're doing something like that. If you're using something like simple batching, you'd also have no users at all because it'd take way too long. The other thing is that because these models are just so big, you can't really scale it horizontally because it's prohibitively expensive. How do we fix some of these issues? There's quite a few different aspects in sort of making them run on the hardware efficiently. We talk here, I just want to point out some of these things, right? One is model optimization. We can just optimize a lot of the operations in these transformer models before we deploy them. So these can be optimized at the hardware level. We have Intel Extension for Transformers and PyTorch for CPUs, and Gaudi 2s, and Optimum Habana specifically for Gaudi 2s. So we can get them to run very fast on these hardware pieces. The other major optimization in this category that you'll see everywhere is quantization, which is that previously I quoted the weights in FP32, but in actuality, when you're actually using them, they're heavily quantized. People found out that by reducing the precision of the weights to something like 8-bit, you actually don't lose very much accuracy at all, and you can run them at this lower precision using much smaller hardware. Even 4-bit quantization has been shown to work, where you can get it to run locally on something like Intel's AI PCs, right? Using these optimizations, you can have a very local, small, large language model running without any kind of expensive hardware components. There's other things like model parallelism, where you're dividing a model into different accelerators in order to best use those models. And that's almost necessary for serving these larger models. This is done through something like DeepSpeed. And finally, to specifically large language models, a lot of the problems I just listed with how a token is generated and how, the sequential nature of it happens, that's solved by using different types of large language models serving frameworks. So stuff like text generation inference, VLLM, DeepSpeed, Me, all of these are algorithms which make that serving much more efficient. So you're not wasting compute. And this is sort of required if you want to deploy a large language model at scale, because horizontal scaling is impossible. You want to maximize the use of your accelerators. And in order to do that, you need one of these frameworks. Keywords to look out for here are model sharding, which is related to model parallelism, block KV caching, and most importantly, something called continuous batching. This is a really specific thing for large language models. It allows you to increase the scale at which you're serving and serve a lot more customers with a lot better throughput. I'm going to speed through these last couple of sections because I don't want to take up too much of your time. Image generation is also a thing that's getting a lot of traction these days, and they kind of run, we have a bunch of open source models for those as well. And these are actually quite a bit smaller than large language models, which makes their computation a little bit different. Also, one thing you'll notice is that when you're building out applications using image generation models, depending on the application, of course, sometimes people are a lot more tolerant to wait. So if you have this sort of less latency sensitive application, you could potentially deploy these models on lower powered hardware and just make people wait a little bit longer. There's no case of large language models where people are waiting for each individual pixel to be generated. They're just kind of waiting for their job to finish so they can continue their task. Application dependent, of course, something like generative fill-in, where they're trying to do art live, that might be something that you want to host on more powerful hardware in order to reap the full benefits of that. So how these models work and how they're different from large language models is that these ones actually take noise and slowly transform them into the image. So you can kind of see in this workflow where it starts with noise. After 5 iterations, some kind of formation starts. 10 iterations, it'll get closer to what the final product is. 15, you really start seeing the structure. And after 25 iterations, each of these requires one model call. You're getting the full image with full detail. Of course, there's a couple things here to notice as well. Each time step is one call to the image model. and quality increases per time step, but it does eventually converge. That convergence rate is sort of unknown. It's really dependent on the prompt and dependent on things like schedulers, which I don't really cover, but they can be quite expensive per iteration. You'll see some terminology out there is that Stable Diffusion uses something called a UNet in order to process these images. And some other models start using things called patch transformers. So if you've seen the Sora papers or Sora details, they'll talk about using diffusion models, using image patches from in a transformer model. So they're talking about changing a UNet to something like a patch transformer. Contrary to LLMs, each model call does not grow in execution time. This is not quite autoregressive, it's more of an iterative thing. And memory usage more or less stays the same. So this is a lot better than the large language model situation, which means that we don't really have to rely on specialized serving engines in order to do this one. The smaller models enable you to use CPUs and efficient graph compilation. You can choose cheaper compute and batch requests in a more natural way. You might consider a job queue if you want to serve these jobs. Retrieval augmented generation. I'm actually going to quickly skip this slide to respect your time. But basically, the idea of RAG here is what I detailed before. And I put some terminology here to help you search to build better RAG systems, because this is such a common use case. The one thing I want to point out here is that if we often, I don't know if it's these days, people still have the same questions, but people always ask like, oh, what should I use in order to introduce new information to my model? The general advice we give is that if you're trying to introduce new information to a model, you probably want to use something like RAG and prompt engineering. Fine-tuning will not really get you to add new information. It's mainly used for behavior change and teaching it new skills. There's a bunch of keywords here for solving each of the individual components, and you might want to look into those if you're interested in building RAG systems. Fine-tuning and pre-training on a platform like this is something that the most notable thing is that this is a much more expensive task than inference. When you're doing fine-tuning, it's pretty much required that you have some kind of accelerators, although there have been instances where you can fine-tune one of these models like a Llama 7B on Xeon CPUs, and we've done that. It just takes quite a bit longer than if you have something like a Gaudi 2 accelerator. Two things to look out here is for parameter efficient fine-tuning and preference optimization. In these situations, the idea is that when you're doing fine-tuning for a 7 billion parameter model, you generally do not have the capability to tune all 7 billion parameters. So parameter efficient fine-tuning lets you train a much smaller subset of the parameters. So for example, for the 7 billion parameter model, you might be only training about 3 million of them. And because you're training such a small amount of the parameters, you can actually run it on much lighter hardware. So here we show we can actually run Llama 2 7B in we can fine tune a Llama 2 7 billion model with parameter efficient fine tuning on 8 Gaudi 2s in about like 5 minutes. So it's much quicker, much more efficient. You can better utilize your hardware. And if you're doing fine tuning, you're basically going to be in that realm. Full model fine tuning is something that I'm not going to get too much into, but basically in order to do that, you're kind of already an expert in that area. And you're looking to basically exploit a huge cluster of GPUs or Gaudi 2s or any kind of accelerator in order to get that done. We have a quick workflow here that kind of balances it out. You can use a pre-trained model via prompt engineering, and that's the cheapest, but doesn't allow for the most customization. Fine-tuning does increase cost a little bit, even when you're self-deploying. and that has the capability to customize it more to your data. And pre-training, as we just mentioned, is a lot more expensive, and probably you don't want to use it too much. Finally, I just wanted to include a quick thing on multimodal models, where these are up and coming models that take different modalities and combine them to get different results. And the way they typically work is by feeding in an image to a image encoder, text into a text encoder, and then combining the results and feeding them into a fine-tuned large language model. When you're deploying these under this architecture, it's not too different than just deploying a large language model. So we can actually use the same packages like TGI or VLM to serve them. It's just introducing this new modality adds this additional layer of complexity. There's a lot of research still being done in this field, so it's a lot less mature than deploying something like a large language model. So yeah, the main takeaways, I sped through the last couple of slides, but the main takeaways I want from here is that a generative AI platform can help you structure how generative AI is used in your organization. We kind of felt that having this kind of structure helped us look at different angles and helped us build different components to hit compliance for our clients. Self-hosting open source generative AI models has many benefits, and the right software tools and platforms can ease the challenges. I detailed a lot of different challenges, and we kind of solved all of them by just looking at the different ways and software packages that are available. This is a non-stop developing field. Right after this, I'll have to check the news to see if anything new came out. But we have to adapt fast. Platform like this kind of allows you to adapt in different ways as you see fit. And with that, I'm ending it. Thank you so much for listening, and I think we're kicking it off to questions now.
Thank you, Richard. That was great presentation, very informative. For everyone who's interested, you can try out Intel's latest platform technologies on Intel Developer Cloud. Access it right here through the QR code and sign up for a free trial. So yeah, so let's go into Q&A. We have, I think we have a few minutes left. So first question, Richard, is going back to slide 20. You can do that. The question is the model weight on that slide related to the RAM memory in terms of what's required and allocated?
Yeah, so it's related to the RAM if you're using CPU. It's related to like the VRAM if you're using accelerators. Every time you generate a new token, you're kind of caching a lot of computation so that the next token can be generated faster. So it does blow up in memory, and that's why you kind of see these innovations in context length, right? Longer context will take more memory. How much memory, that's kind of complicated because it's divided between a lot of different accelerators as well. But yeah, it does relate to RAM required.
I think maybe it's the next slide, Richard, that they're referring to. But I think same point applies in terms of what you said here. I think that's
it's still the same point.
Yeah.
Mm-hmm.
Okay. Let's see, the next question. I don't know if it's a fair question, but so it's considering all the possibilities with GenAI, would companies no longer need to hire data scientists or ML engineers and instead, invest in GenAI tools? I don't know if that's a fair question, but
well, I hope they still need to hire data scientists and ML engineers. At the moment, I don't think it's quite a replacement. We definitely see a lot of these tasks being automated, but there's still so much to think about in terms of how we use these models and how we responsibly build these applications that I still think there's a lot of value. I mentioned before, I don't think it's a replacement for everything. We might not be training the same models anymore, but there's always use for training very specific models that work well for specific situations, whether this is hardware or just seeing performance that's better, right? You can easily probably build like an image classifier that might be better than using something like, one of these stable diffusion models or something like that. So it's not quite the point of replacement yet. Maybe in the future.
Okay.
Hopefully not.
Okay, so I think we'll have time for two more questions. What are the modalities besides text and image? Other modalities are getting used? And would time series data be considered a different modality?
So different modalities in this case are like we've seen audio being used, and there's already models for audio, right? Any modality here would just be some kind of different format than you normally take in, right? The most common modality we see is text, and then images, audio waveforms. And whether your question of whether time series is something that can be considered a modality, there's no reason why it can't be. Time series are just a sequence of numbers, but that sequential pattern probably is carrying a lot of information. So yeah, there's no reason why you can't, train a model that takes a time series and codes it and combines it with some text encoding that you can answer questions with, right? You do have to train that model yourself because it's probably not something that a lot of people have thought about.
Okay, so let's wrap this up. I know there's a few more questions that I think we can try and answer offline. Lots of people are asking, how do they get a copy of the slides? So we'll make that available to all attendees and all registrants in a follow-up email. So please look for that. And then I will say, let me remind you of our next webinar, which will be a really fun one. It's called Beauty of GenAI in Retail, where we'll hear from iterate.ai and also Elf Beauty to really come and tell us how they're using LLMs in a real world application. So once we close this webinar, I want to thank you for coming. And there'll be a survey that will pop up after we close. And I hope you'll take a minute to fill out that survey to give us feedback and tell us how we're doing. All right. Thank you very much, everybody. We'll see you next time.
Thank you.